All right, so here we're in chapter 4 on exponential and logarithmic functions. This is section 4.7 on exponential and logarithmic models. So let's look at the characteristics of an exponential function. So we know the function is going to look like something a naught e to the kt. Now it's going to be one-to-one, so no matter how many times we draw a horizontal line, it's just going to hit the axis once. And we're going to have a horizontal asymptote at y equals 0 because it's going to either increase from 0 all the way up to infinity or decrease depending on if it's a decay or a growth, but it never touches that 0. Our domain, because it's that way, is going to be from, negative infinity to positive infinity. But our range, because we have that horizontal asymptote at 0, it's going to be from 0 to positive infinity. It's not going to have an x-intercept because it's never going to actually cross that axis. Our y-intercept is going to be 0, comma a naught. So whatever our a naught is in our original equation, that's going to be here. Now it's going to be an increasing function if k is greater than 0, and it's going to be decreasing if k is less than 0. So it all depends on what our k is. And then we have a couple points. We have 1 over k, comma, a naught e, and we have a negative 1 over k, comma, a naught over e. So those are the 3 points we can get just easily using the numbers from our function that we're given. And again, our k naught greater than 0 is increasing, our k naught less than 0 is decreasing. That's a decay function. And that means this one is not going to be the same as this. So this is going to be a negative 1 over k, comma, a naught e. And down here, it's 1 over k, a naught over e. So our y is going to be the same for both of them as far as the top one is going to be the same, but it's our x that's going to be different. So this one's a 1 over k and this one's a negative 1 over k because we're on the decay side. So we start high and then we go low. And here we start low with a negative 1 over k and we go high to the positive 1 over k kind of thing. So that's going to be kind of our shapes we're going to be looking at for our exponential functions. Now, the modeling of the exponential growth and decay, again, our A naught, that's going to be our value at time equal to 0. So, whatever, we're starting with 50 bacteria and we're doing exponential growth, then it's going to, grow exponentially like this. Or maybe we have a radioactive element and it's going to decay and it's going to go over time. So that A naught's the beginning amount we're going to start with. And then again, our K naught, our K is going to be greater than or less than 0, depending on if we have a growth or decay. And then our time is just T, and that's just going to be that. And our K is going to be the growth rate or the decay rate. So that's going to be our rate of decay or growth. Okay, so that's how we get these values. Now, if we notice, our K here is 3. So remember, that was 1 over K, so it's 1 over 3. Now, if we plug that in for x, that gives us, a 1, so e to the 1, so that gives us 2e to the 1. So that's how we get this. And if we have this, we get negative 1 over 3 and 2 over e. And again, that just follows what our thing was. It was a naught over e, and here it was, a naught times e. And so that's where we're getting that because, these are 1 over k, and that was the k value. And the same thing goes here. Here, it's the 2 and it's negative. It's going to be the 1 over k here and negative 1 over k here. So it's kind of opposite. And so because it's decay, we're just using that 2 part. And so 1 over that's going to give us a 3e. And here is going to be 3 over e. And that's because that's going to be our 3. That's our a naught. And then we plug that in and we just get e, and it's going to be e in the denominator here. Now, when we're working with these are going to be looking at orders of magnitude. So we're going to look at huge numbers because, when you have an exponential growth or decay, you're going to start really small and get really huge. You're going to start really huge and get really small. And so we need to talk about what is the order of magnitude. Well, it's some power of 10. And so we usually express this in scientific notation. So we would have something like this, and we would say the order of magnitude is, and the order of magnitude is the piece over here where it's times 10 to the power. Okay, so this is the order of magnitude of 10 to the 15th. Now we really don't care about this part because it's going to be really minuscule compared to what this is, and so we're really worried about that order of magnitude. Now, sometimes you might say, at maybe time 0, we'll have some order of magnitude of say 10 to the second. But at time 12, we might be 10 to the, I don't know, ninth. Okay, so we've got a huge order of magnitude difference. And what we're going to say is, well, the order of magnitude difference here basically is just going to be 9 minus 2, or that's 7 orders of magnitude. Okay, so it's gone up by 7 orders of magnitude. Now, can we do a different kind of plot? Yeah, we could plot this on a log plot. So a log plot, we could plot this, and maybe this is our 10 to the 2, and this, or well, and maybe we're not going to plot these, we're just going to plot something, and maybe here we have 10 to the negative 15, and so we could figure out how many orders of magnitude it went up here, and it's going to look like that, and maybe somewhere here in the middle we have, I don't know, 10 to the negative 5. So, we can go different places and figure out the order of magnitude between them. And again, this is called a log plot. If we just plot it on this linear model, and we can just figure out how many spaces in between here to here and here to here, and that's going to be our order of magnitude changes. Or we can just take our 9 minus our 2, and we get the 7 orders of magnitude here. All right, so here we're going to have an actual example, and we're going to, again, use our function we had. And I don't know, if maybe since this is population, maybe we're going to have P of t is equal to our A naught e to the kt. And so what we need to do is figure out what we're getting based on what they give us. So it says a population of bacteria doubles every hour. Okay, so we're doubling, and time is an hour. Okay, so that's something we know. Now, if the culture started with 50 bacteria, well, hey, what's that going to be? Well, that's going to be our A naught. Graph the population as a function of time. Well, before we can do any graphing, we actually have to get the full function written out. So what do we know? Well, we know that A naught was 50 bacteria. Okay, I'm not going to write the bacteria part. And it's going to double every hour. So if we double 50, what do we get? We get 100. So let's start plugging things in here and solving for what we need. So if we double it, we get to 100. We started with 50. E, now the K is the part we don't know. That's the factor it grows by. But we know that it doubles every hour, so we know that that's a 1. And so what we're going to do is we're going to solve for our k first, then we can plug it in, and then we know it's going to be 50e to the some k value times t. And then once we get that k, we can graph that. And again, we're going to graph it using the calculator, not by hand, because that's going to be a little hard by hand. And so what we need to do is we need to solve this for k. Well, first things first, let's get rid of that 50. And so 100 divided by 50 is 2. And that equals e to the k, because k times 1 is just k. Now, how do I get rid of this? Well, I'm going to use logs, because if I use a log, I know the power rule says I can bring that down. But if you take a log on one side, I have to take it to the other side. And so that says ln of 2 is equal to k ln of e. Well, if we've been doing any work, we know ln of e is just 1. So k is equal to ln of 2. Now we can put parentheses around it or not, it doesn't matter. So that tells me that this k is going to be ln of 2. So p of t is equal to 50 e to the ln of 2 times t. And so that is going to be what I plot. So let's plot that and see what it looks like. So we go over here and say, okay, y equals, and we say it's 50, and it's times e to the ln of 2 times x. Now, we don't have a t here, we have to use x, so that's okay. So we're going to use x, and we can graph that. And looks like we could probably do a little bit better here for our window. Maybe we don't need to go from here, but we can go up to, I don't know, let's go up to 350. I don't know what we need to go by. And let's go 50. And so now let's see if that helps us any. Yeah, so now we can see that that's kind of the shape of our graph. Now, what if we wanted to find some different times on here, kind of to start looking at our orders of magnitude? Well, we can hit trace, and let's say at x equals 0, we have 50. Well, that's what it's supposed to be, so that's a good thing, because that's supposed to be a naught at 0. What if we looked at, 12 hours later? So we type in 12. Well, that says we have 204,800. Okay, so that's that 50 in 12 hours went up to 204,800, 204,800. Okay, so it's gone up pretty significantly. And then we're not even on a chart. It's going to be so far above here we can't even get to it. What about 24 hours later? That's another number that sometimes is used. And we don't have enough on our window, so that means our window needs to go up. So let's go up to 30. And so now we can trace again. And so we'll do 24 hours. Well, look at that. Now it's gone up to 838,860,800. So we've gone up to a huge number in 24 hours, starting at, time zero, we were at 50. So, it's like, boom, just gone straight up. That's why this is called an exponential function. And so let's write those down. So we know that at t0, we were at 50. At t of 12 hours, just 12 hours later, what do we have? We had 204,800, and t of 24, that was 838, 88, or no, not 88, it was 86, I believe. Let's write that a little nicer. We had 838, 860, 800. Yeah, I think that's what it was. And so if we put that in scientific notation, that's going to be just 5 times 10 to the first. That's going to be 2.0. Well, here we only had one decimal, but we can put 2. Maybe we could put let's do 2 up here too. Maybe we have 5.0 times 10 to the first. There we have 2.0 times 10 to the 1, 2, 3, 4, 5. And here we have 8.4 times 10 to the 1, 2, 3, 4, 5, 6, 7. Wait, 1, 2, 3, 4, 5, 6, 7, 8. 1, 2, 3, 4, 5. Okay. So, from here to here in 12 hours, we went up 4 orders of magnitude. And from here to here, we went up 3 more orders of magnitude. Okay, so in that first 12 hours, it went up 4 orders of magnitude. Next one, we went up 3 orders of magnitude. We could do more and see what it went, but it looks like every 12 hours it's going up, significantly, because we went up from 204,000 to 838, almost 839 million. So we're going up by big orders of magnitude when we have these exponential type functions. Okay. All right, so let's pause there and we'll come back for more.